our shell program, welcome back again. Today we're continuing work on the shell program, Shelldon, and we left off looking for a mascot and put that up to a vote on both the YouTube and the Twitters, or X, or Twex, Twexer. Maybe we can start getting people to convince to call it Twexer. Maybe. Although I highly doubt it. Alright, let's get back into it here. Whoops. There we are. Alright, so we put her up to a vote on YouTube. And Little Shelldon won 2-1. But then over on Twitter, Big Shelldon got 2 votes, and small one got none. So we're going to go with the Big Shelldon, and here he is, and we've got him converted to a ASCII art. So if you're not familiar with what that is, it's drawing pictures with characters on the screen, and kind of like that. So here's our Shelldon mascot and ASCII art to start with. And what we left off at, was working to make it to where when we enter a command, we get question marks. Let's see. Yeah, we're good. Excuse me. So we can put a question mark to get the list of commands, or we can execute the commands. We can run the latest batch of test code, which is our card program. And these were supposed to be LED characters, but they look very much more stylized, and really wasn't what I was going for. So we're going to have to revisit our big LED library and maybe redraw these. Look at that. That's just all whacked out of size and shape. That's crazy. Now, we were testing before that our random number generator. So if we quit, we're at a halt in the test program. But if we continue from there, we fill the screen with random numbers. Occasionally it hits the bell character. So I guess that's all the little boop, 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 boop. I don't hear any randomness or any pattern in that. Well, in any case, we will restart. So, where we last left off is we have a shell program, and that shell program allows you to do things like this, right? So what we wanted to do was have a way to where the shell program is responsible for looking at the command you typed in and chopping it up into words and passing it on to the next command. So and I wanted to do that in a way where we can just add things as we need to. So if we take a look over at the shell program, you'll see that we had our command map, right? So we had our define the command map, then we have the help command, which up here is defined as question mark, a string that contains 1 character and ends in a 0, so just a 1 character question mark. There's its help message. Then we have the ASCII command, and so we have the command, the pointer to the function that executes that command, as well as a message to tell you what that command's all about. So we define those here in this table by just bringing them in one after the other. So the clear command, the clear function, the clear message. There's all very similar. The command is just a C, and the message is this little help message. And to give you an example of adding on a file, so here's our shell test function file. This is where we do all the cards and the random screen. And at the top of this, we've defined the test command to be the word test. Then the message just runs the latest test code. So we define all that. Here's our test function definition. And we put those in an external includes command, or external commands include files. They're all assembly files in my world, but you can include one file inside in another, and thus not have to have everything about a file in a single file. Seems kind of redundant, but anyway. So let's do a quick check here. Checkity check yourself before you wreckity wreck yourself. There we go. Let's say hi to the chat. Hi chat. Don't get all noisy at once. And who cares about spelling? You know, it's a chat, right? Nobody spell checks anymore. So this external commands is actually included here. And where'd it go? Where'd it go? There we go. Here's our external includes. And our external commands are placed here. So external commands only includes the new items for our command shell. Like we just added the EUP invaders command. And there's the test function, and then external includes the files that we need for those external shell commands. And by cutting it up into files like this, we don't have to edit this one, which is long and complex. We can simply add the commands here. So let's go ahead and we have the space invaders, or the start of our EUP invaders. So that command is EI. And sure enough, there's our little guy. Ooh. Uh-oh. He's going way too fast, isn't he? There's no way I'm gonna... way too fast. Let's see. We're gonna have to slow him down. Let's see. So, we know he's... Oh, and that's a problem. We're not supposed to be seeing those anymore. Well, that's probably part of the failure to slow down enough. So let's go ahead and take a look. Fix that up. There's our EUP invaders code. And let's search for sleep. And what we did was we modified sleep. And it just was taking too long each. So instead of loading one, we'll load a constant of, let's try 10, just make it 10 times slower. There we go. Back to the shell to run it. There's our compilation step. Our entire program is 2,733 bytes. And we're taking up 585 bytes of data to manage it. And then we print out our assembly file. So anyway, here we are. Let's do it here, where we have a whole lot of shell to shoot up. Oh, well, it's flying slower. Perhaps not quite slow enough though. Weird. And it doesn't seem to be detecting when I go kaboodie. Well, leave it to me to go off topic in the first 5 minutes, eh? Well, what we wanted to do is actually discuss how we got this shell program operational, because turns out when I designed the instruction set, I didn't really think about doing a function pointer. So all of the jump commands, so these are all the jumps based off of different conditions, and then for long and short jumps, two things. Over all this time, I found out the short jumps are about useless. So we don't really need short jumps on the conditionals. Really, this whole row here is pretty useless. But here's our call, our function call command. And that is not really complicated. It takes the current address that you're sitting at, puts that on the stack, and then falls through to a long pointer. So it looks at the next 2 bytes. I should say a long jump. So a long jump looks at the next 2 bytes and uses those 2 bytes as its next destination address. The problem is it expects those 2 bytes to be in ROM, not in RAM or in the DR register. So one of the things I'm thinking of is perhaps this CAS here instruction that we really haven't used, because there's no point in making a function call to a short address. So, you know, not very useful. So instead I might retask this instruction to do this a little bit more, to do a call to an address in the DR register rather than expecting it to be in ROM. But the way we got this to work at the moment, probably less than ideal, is we have a we make a call rather to a function called call function pointer, right? And so we look at, let me get the right file here. So when we run through the loop and we say, oh, you typed in EI, that was the EUP invaders command. So now we want you to go to the EUP invaders main loop function. These 2 bytes represented by this symbol have to be put into the ROM in an existing long call or call instruction. So what we're kind of doing here is just a little bit of cheating, because if my ROM was truly read-only, then I wouldn't be able to write bytes to it, and this would completely fail, which is why I'm thinking maybe we'll create an instruction for it. But what happens is, whatever location is in the DR register, when we come into this function, we save off both bytes into the A and B registers. Then we load up this location in memory, which is actually within the code itself. And then we use the literal command to put the instruction for a call, not the actual call itself. So the assembler won't try and, because the assembler, if I put call here, the assembler will expect the next 2 to be some number of bytes or some symbol. And so it's just easier to put in the literal instruction 96, which is this one, the call command, and then 2 blank bytes as placeholders rather. So, oh, we have some new viewers. Shout out to our usual viewers. Let's see who all we got going here. Oh, quit that. Apparently when my mouse gets close to my phone, I get all sorts of noises, or headphone cable rather. So we just wanted to have a quick shout out to Ella and Julia and Gabby, Joey, and Chris. Make sure I get all those names right and get all you in. Thanks for watching, being the super fans that you are. And let's see. All right, so we got in here. We set this up with a sort of a hacky version of a long call, then our 2 bytes. And these 2 instructions here store into EEPROM the A register and then store into EEPROM the B register, actually overwrite these 2 bytes in ROM, and then we make the function call to it. This is fairly hacky and works, but I really wanted to reserve the writing to the ROM area. And the reason it's capable of doing it at all is eventually I want to have something like a hard drive. And to do that, it's going to be in the ROM. And so in a real system, you'd probably have a separate batch of ROM for your program from your actual hard drive, or batch of files, I guess I should say. I might add, you know, let me know down below if you think you'd like to see me actually implement a hard drive, like interface to the actual hardware on my PC. That'd be an interesting implementation or emulation feature. Let's see. So, it's a little hacky there, but it works. And let me show you that in action. Let's add a halt and a no-op. That essentially is a breakpoint for me. Come back to the shell, run the shell. Here we go. And now if we want, I'm gonna call that, let's do it for the help function. So question mark. Now we've called this, and our DR contains 2093. Right? So we're gonna load into the A register the R register. So that 93 goes over here. Then we're going to load the 20 into the B register, and that's so the DR register is free for us to load up the address of this location in ROM, right, to FB, and you'll actually see it here. Here, right down here, is the literals we put in, the 96 and the 00. So now if we increment our function pointer, that skips over the 96. Now if we store into EEPROM what's in A, here's our 93 over here, increment, store our 20 here, and now we're about to make that call. So we make that call, and sure enough, we're inside the help function. So in a PC, that'd be called function pointers. It's still function pointers, but I don't know how often you implement function pointers in assembly. But in this case, it's very helpful because, like I said, we get to divvy up the application, and later on, if you want to add a command. In fact, let's go ahead and add a command, why not? Let's see, some of the functions we used to have were things like, we had the game loop, right? Let's see, the boot monitor, we had, what to do? And to clear screen, we got that moved over. This was the EUP out game, which I'm not sure that does much of anything anymore. Let's see, let's run the boot monitor and see what the G command does for us. All right, quit that. G. Oh yeah, there we go. This is our little sort of snake game, if you will. All right, so that's from our old program. Let's move this over to our new one. Sorry, couldn't get to the mute. There we go. Oh, that was better. All right, so this is our silly little snakish game, right, where we just moved around, didn't do much interesting. But we can quit out of that. Let's take a look here. So our game was EUP out, right? So now to add the EUP out game, I guess it's snake game anyway, to our shell, we don't actually have to deal with the shell at all. We'll just need to have three things to write here. We will need the EUP command, we will need the EUP function, and then the EUP message. That's what we need in external commands, and in external concludes, we will uncomment out our EUP v2, and then we can actually open this real quick. Set our language. All right. So a couple of things we need before that, right? We needed to define the EUP command. That's going to be a string. EO maybe? Sure, why not, right? EO sounds good enough. Then we have to define the message, and that is going to be EO colon the EUP out game that is more like Snake. Save all that. We can just run back over to our shell, get it running, and now clear the screen. Whoops. Well, that's going to be annoying. Let's comment that out. Get going again. Alright. Clear the screen. Now when we do question mark, our EO option is added right to the list. And now we can do EO, and here we are in the little Snake game. Isn't that convenient? So what we're aiming for is the ability to add commands as needed. I want to eventually make it to where that table is essentially however big it's necessary. Although, you know, realistically we're probably not going to have that many other functions here at any given time, because most embedded systems really only run one main program. In this case, we're kind of building it up and using it like an old school PC, which is fun, but probably less than totally realistic as to what you would normally do with these kinds of processors. So let's see, what else do we want to do? Let's see, we showed how we had to hack it. Now, if you want to see how those commands are actually implemented inside the processor, that is a series of ROM files called the sequence map and the sequencer. Let's get those both set up. I'll spread this open a little bit more. Kind of an inconvenient position for my floating head here. Let's move that around just a smidge. Not display capture. Always doing display capture. Not, there we go. Let's move me over here. I can live over here for the moment. That way we can have a lot more screen. There we go. Alright, so the reality about our processor will be similar to most other micro-coded processors, is what's really happening is every instruction or every pulse of the instruction clock advances a pointer within the sequencer. Now, the first 10 locations in the sequencer are used just to set up the processor and get to the point where it can load what we consider to be the main application. So the first thing it's doing is setting up the zeroing out all the registers for us, setting up A, B, R, D, P, I, all of the registers to 0. Then except for the stack pointer, which we want to be FFFF. Then after we've set both the S and the K pointer to FF, we'll output enable the EEPROM and say we want to load the instruction pointer at the base of ROM, which is where we put main. And you see that every time we create a program, the very top is write out main and then change the origin to 16. I say first 10 instructions, it's actually 16. So here's the first 16 instructions. They do all that zeroing out of things, which probably wouldn't be necessary in a processor, but is thorough, if you will. And then we load the instruction register, and every time we load the instruction register, we take that instruction and we look it up in the sequence map, the instruction register sequence map. So for example, the first instruction at main in the EUP shell command, first actual instruction, gets all past all these includes and everything. But the first actual instruction inside the function main, so let's go to main. Oh, there's a lot of calls to main. But let's get down here. Here's the actual function call to main. So the very first instruction in main is to do LDR, which is converted by the assembler to one of these numbers. LDR, here we go, is 7.6. So 7.6 in the sequence map is located 0, 1, 2, 3, 4, 5, 6. Right there. LDR is 00B0. B0 is used as an address in the sequencer. So down here at B0 in the sequencer, we actually do the microcode instructions for loading DR. And what LDR does is it takes the next 2 bytes in ROM and puts them into the D and the R registers. And you can see here we move the instruction pointer to the next location. Then LRE. So I've renamed some of these instructions over the years, so sometimes I have to double check what these things mean. LRE, yeah, load into the R register from EEPROM. Then increment the instruction pointer, load the D register from EEPROM, change the instruction pointer one more time, and then load that next instruction. So we load the next instruction after LDR, and that's CAL. That next instruction, CAL, is here. It's 9.6. Again, the assembler has replaced the CAL with number 9.6. So if we look up 9.6, the call instruction, it starts at 5.0 in the sequencer. The last 2 bytes here, or the last byte here is the instruction, the location within the sequencer to start doing the process necessary to execute an instruction. So in this case it's 5.0. In the LDR it started at B0. And you'll see that there's a lot of places where the number is the same. And that's because a lot of instructions do much the same thing but have different registers. So these first 2 bytes are utilized to instruct the sequencer logic what registers to deal with. So you'll see there's a lot of overlap until we get down into the sort of one-off instructions that really only affect one register. But the architecture was done thusly so that we could have a small number of sequences that cover a large number of instructions. Because there you go, there's 4.8. That's perhaps the most used actual sequence in the sequencer. So we load up the CAL. We looked up CAL, right? That's 50. We go back over to the sequencer ROM, look up address 50, and that's where we start the call function. And you'll see here we actually, as I just sort of described before, the jump long, or jump to the next 2 bytes in ROM, and call are pretty close to the same thing. The only difference is a jump just jumps, just changes the instruction pointer, goes to the new location. Call is saving the current instruction pointer on the stack, and then it falls through to the long call function. Now, in order to do a function pointer, instead of the call reading from ROM, it needs to read from the D and the R register. But the downside that I'm running into is this part. We save the IP on the stack, but that means we're saving the current location. In other words, when we make the call, let's see, here's the best way to look at it. When we make the call, we're storing this location on the stack, and there's 2 more bytes. So upon return, we have to get past those 2 bytes to get to the actual next instruction. And right now, the responsibility for getting past the 2 bytes is left up to the return instruction. Where's the return instruction? There we go. There's our return instruction. So hard to decipher without being familiar with it, but you see this kind of pattern of C0s and then C0s and CO2, and what these are doing is doing that increment to increment past the 2 address bytes to get to the new instruction byte. But what I should have done is, upon the call, increment the instruction pointer twice and store that location. By doing that, then when I do the function pointer style, the return can be the same sequence. And since these sequences can just fall through, yeah, we would have a different sequence for the long call. And instead of jump long, it would be jump long EEPROM, it would be jump long to the DR. And when we do that, we don't have to increment the instruction pointer twice because it'll be a single byte instruction. So we'll definitely need a different call, because instead of storing the current IP on the stack, we would need IP plus 1. And we want to do IP plus 1 for the function pointer call, and we want to do IP plus 2 for the long call. Well, we don't have to decide today. But just in summary, the whole system is a series of lookup tables. And that's essentially how it operates. Each one of the bits in these words mean things. So, for example, if we wanted to load the instruction register, that is bit 1 of this nibble, of this 4-bit. So we can do different things and overlap them so that they happen in parallel. Increment and decrement the stack pointer, reset line, system operations flag, all of these things are defined by the pattern within the sequencer ROM, which is 32-bit, 256 32-bit words. And let's see. Let's see. I think that was all we had for the design for now. Let's see what else we want to go through here. We added a function to our shell by adding the yup command. You know, I'm still a little wondering why our yup invaders code it's running too fast, and maybe it's because it's running too fast I can't get it to go boom, but it never seems to go boom. And it's supposed to be going boom when it reaches near the top of the page. So let's see, let's move myself back over. That's always fun, right? Totally interesting part of the stream is watching me move myself around, right? There we go. Let's put it over there. We don't need these scroll bars. Something like that. That'll work. Alright. Cruising right along. Let's see. Okay, so we're going to go back over to the shell. Shell's running. And then it was, oh, we can always hit question. It was yup invaders. Yeah, there we go. Now, he's still, oh, there we got a couple of explosions out of him. Or one, anyway. Woo! Alright. Now let's see what we want to do with this guy. Well, right now, what we're doing is we're saying if the way I determine that it's time to go boom is if I fire a bullet and then fire another one while the first bullet is in the right location at the right height. I'm not nearly as good at this as I used to be, and it's only been a week or so. Anyway, that kind of logic for when it should go boom isn't particularly useful. We need to find a different way of determining that the bullet hit the bad guy. And let's see what we got here for that. Hang on just a sec. Alrighty, I spare you all that noise. Let's see. Alright, we got our moving a character around, we fire. Let's slow that down some more, shall we? So, yup invaders code. Let's make it 16 instead of 1 or 10. And back to our shell. Build and run. And actually, go ahead and just refresh. Yup invaders. Now we got lots of. Yeah, that's a little easier, eh? Come on. We're poking him in the eye. We're gonna destroy his antennae. Oh no, not Shelldon. Oh man. Sorry, I'm having an itchy FaceTime today. I don't know what the deal is. Alright, what else do we need to do here? I'm trying to get that @ sign. There we go, I got him. Alright. So let's see. Yep, invaders code. We draw the good guy, we draw the bullet. Checking the port for a key pressed. Waiting again. So this is essentially the main loop. We rest a little while. We draw the good guy, we draw the bullet. And the bullet knows. In the draw bullet, we determine whether we need to go check for no boom, and it's just easier to check for the bullet missing than it is for it to check that it hit. And that's because we're just doing a range check to see if it is within this row and it's within this column kind of thing. Which, you know, okay. Let's see. So if we have single character bad guys, it's pretty straightforward, right? My single character bad guy intersects the bullet, single character guy goes bye-bye. If we have a grid, if we have a bad guy that's 3x3 characters, then, and presumably the center, his location is the center of that, then we would have to set up a range to say within this range and that range, and that would all be based off of the bad guy's position. Let's see, what is our bad guys anyway? Invaders code. Let's see, you don't need the sequencer stuff anymore, I don't think. Or yep out. So let's find our Yup Invaders assets. There we go, these were going to be the shields, and where we would hit a block and it would degrade. Would that be that straightforward? We'd have to go through a list of blocks. There could be a block at any given position. So we need an array of blocks. So I originally thought I was going to define a shield, right? And then let's put that in my language here. So I was originally going to design a shield, right? These are the things you hide under, and then as they get hit, the blocks degrade, right? They go from solid to weaker, 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 and then they're gone. And I suppose that's still doable. Let's see. Here's our other spaceships or other bad guys. Here's our good guy, our explosion. There's our shots fired and shots on target. We're going to work on our big LED anyway, so let's go check out the big LED. I didn't really like the actual graphics that we got from that. Programs, display lids, big LED. View our language. So these just didn't look as good. So we really want something that looks truly more like the old school LEDs. So let's see. There's our ASCII table. Oh, I'm overlapping myself. Let's fix that real quick. Alright. And let's see what we want to do. Maybe these little half characters are going to be what we need. Because DE and DD, all these guys here. Right, that's the bottom, the sides, the top. Is there a middle one? Let's see, do I have a D command? Nope. The D command is unknown. That was one of the commands in our original EUP invaders. Or not EUP invaders, in our original monitor program, which I no longer have loaded. Oh, there you go. And D was display hex values, which is way down here. Oh, display hex values. Play hex values. Play hex values. This is why you should comment your code. So when you come back to it years later, you're like, what? Oh, play hex values. That's the sound feature. Right. So let's put a little differentiator between the functions here. And let's just go ahead and snag both of these and let's put them in our other. Copy that code. Put it over here in the shell, way down after main. Now we have those two functions here. And just for, you know, keeping things together. Let's see. Might as well. Display hex values command, and that is going to be a string that is a lowercase d. Then we're going to display hex values message. That is a string that says d:, displays the past of hex values as characters. There we go. And oh, don't forget the end of the string there. So display hex value command and display hex value message. Save that off. And way up here at the top of the loop, after we've brought in, before we bring in the external commands, let's include, well, we'll keep it in order. So that's C, display X value command, right? Display X values the function, display X values the message. So that should have us sure enough. There we go. So the reason that function is there is so that we can say things like D, and then if we put in this F1. Oh, let's see. Nope. See, now we need the space. DF1, and it doesn't work because it's off by a character. So let's put D. If we do space, it'll have. I think it'll read that as nothing. Let's try F1. Nope, not quite working. And I believe the reason for that is previously it was expecting it to be like this, DF1, and it would just print the character for F1, right? Now it's got to have a space between the D and the F1 because that's how our new commands work. So for display hex values, there we go. Display hex values. Let's see. There's our temp. So first thing we do is we load up the temp variable and set it to 0. Then we load up the indexing variable and we set it to 1. Excuse me. And then we load the command string and we add our offset. So can we get away with just increasing that offset instead of loading 1? If we load 2, let's see if that's sufficient to make her behave. D, F, E, need the space. Yeah, there we go. Now we got it. So we can, let's see, we were going to do the characters. So if we wanted to do the 8 of an LED digit, it's going to consist of a space, probably DC, this character, and then another space, and then a carriage return, and then we are going to have DB, no, DD or DE? Oh, yeah, I think DD, then a space, and then DE, carriage return, then that doesn't really work either. It doesn't give me the look I'm looking for, I don't think. Well, let's see. That's kind of right? Let's see, we take that. Let's just take this whole command, duplicate it, and then we want to kind of duplicate that. I don't know. Yeah, I guess so. That's going to be 1, 2, 3, 4, 5. That's going to be big. So we got those, right? Now if we just duplicate, yeah. So hang on. Instead of this space, right? What if we used DC? Oh no, FE. FE looks like the one I'm looking for. So this would be space FE space carriage return space df space and carriage return just for fun. Oh, not quite. That was not quite what I was looking for. So we were right up until this last line, right? Right, so that's kind of, ugh, I don't like it. It's gonna be way too big. Instead of DC, 20 FE, 20 OA, DD, 20 DE, OA, 20 FE, 20 A. There we go. That's still 1, 2, 3, 4, 5. 3 by 5. That's big LEDs. That would definitely be a big LED. So it consists of all of this. And then the next row down would be a duplicate of this middle row of DD 20DE. That, let's see, yep, almost there. And let's see, so we're going to have this whole thing. Then we're going to have a space, another FE, another space. There's our 8. That's what a full LED kind of looks like, right? So let's see, make sure I'm visible here. All right, so that's more like an LED letter, right, or number. So I don't know. I mean, it looks a little skinny-ish. Like, what if we were to replace? So I'm just gonna copy that off, save that for now. There's our big LED library. Let's see. Table. So this will be a different kind of big LED, but in any case, let's store that command here temporarily. And instead of DD and DE, instead of these guys, which are kind of skinny sides, let's see what it looks like if we use DB. So copy all that down. Well, let's do it this way. So DD is going to be replaced with DB. And same thing with D that. DE. No, DB rather. B. That should be it. What? Come on. That's an ugly LED, don't you think? Yeah. Ugh. Let's keep with the original, shall we? So the beauty of this is to erase any given element. I just replace that special character with a space character. And the downside is it is 3 by 5 instead of 3 by 3, so it is extra big, I guess. So that'll be a task for next time, or task for the interim, which is we're going to use this new style of LED character instead of this not so beautiful one that was shown, where was it? That was the test code. And it showed each of the digits once for each loop through. But you see, those look not at all like LED digits, do they? And man, is that beeping loud. Alright. Well, you get the idea. We're going to come back in the next time. We'll have these LED digits built up better. And then hopefully in the Up Invaders game, we'll have a score to go for a total hits and misses, or totals fired and misses, and something like that. Some sort of score to go with the game. Or we could go on and do something like blackjack. And even with that, we'll need some sort of numbers to show you your bank and how much you're betting and all that kind of thing. And, you know, we could do with just standard characters, but that's just so small. We want it to be big and bold and beautiful. Alright. Well, thanks for joining me and watching while you did. Again, shout out to the kids. Let's make sure that we don't forget anyone. Oh, Jesus. So, thanks for watching, Ella, Julia, Gabby, Chris, and Joey. It's good to have your feedback and good to see you watching. And we'll talk to you all later. And if you like this kind of content and you're interested in how computers work and low-level processor kinds of things, feel free to like and subscribe, and make sure to leave that thumbs up for us, and ring the bell for notifications, because you never know when we'll be back. We're trying to make it a little bit more common, more weekly or so, but we'll see how things go. So thanks for joining us, and we'll see you all next time.